Okay, let's unpack this. Welcome to the deep dive. Today, we're plunging into something really quite fascinating in statistics, Stein's paradox. It's honestly one of those results that just seems to fly in the face of common sense.
It absolutely does. It catches almost everyone off guard the first time they encounter it.
Right. So imagine you're trying to estimate, let's say, three totally separate things, like the average wheat yield back in '93. How many people watched Wimbledon in 2001, and, I don't know, the average weight of a candy bar?
Okay, three very different quantities.
Exactly. Now, your gut and probably most stats 101 courses would tell you just estimate each one on its own, right?
That's the standard approach. Seems logical.
But here's the kicker. What if I told you you can actually get better estimates on average for all three combined if you estimate them together?
Uh-huh. That's the paradox.
It sounds completely mad. Like, how could knowing about wheat yields possibly help you estimate the weight of a Snickers bar more accurately, even indirectly?
Well, it's not quite like that, but that's the essence of the confusion.
So our mission today is to figure out why this seemingly absurd idea isn't just true, but actually really important for how we analyze data, how we build AI models, all sorts of things.
Exactly. It has surprisingly broad implications.
We've got some great source material, academic papers, explanations from mathematicians trying to make it intuitive. We're going deep on maybe the most counterintuitive thing in stats.
Sounds like a plan.
So when my gut screams estimate separately, and you're saying that's, well, not the best way for three or more things,
Yeah.
what exactly is Stein's paradox saying? Lay it out for us.
Okay, so the core idea is this. If you're trying to estimate the means of three or more independent variables, and crucially, they're normally distributed, or close to it.
By classic bell curve.
Yes. Then it turns out it's always better, on average, to shrink those individual estimates towards some common point, like the overall average, or even just zero.
Shrink them, you mean adjust them.
Adjust them, pull them slightly away from their measured value towards a central value. The standard method, just using the raw measurement statisticians, call it the maximum likelihood estimator, or MLE.
Okay.
That method is actually technically inadmissible in three or more dimensions.
Inadmissible, that sounds serious.
It is, in statistical terms. It means there's another method in this case, the James Stein estimator, that performs demonstrably better, consistently.
And better means?
Better means having a strictly lower risk. Usually we measure risk here by the total mean squared error. So you square the difference between your estimate and the true value for each variable, add them all up, and average that over many, many hypothetical tries.
So lower average error across all the estimates combined.
Precisely. It's not about getting any single estimate perfect. It's about improving the overall accuracy of the set of estimates.
Okay, I think I'm starting to see the definition, but it still feels wrong. My estimate for the candy bar weight gets better because I also estimated wheat yields and tennis spectators. It feels like information is leaking between unrelated things.
That's the crux of why it's so baffling. And you're right to push on that. Let's be really clear. You're not necessarily getting a better estimate for the wheat yield in isolation or that specific candy bar by itself.
Okay. That helps.
The improvement is in the total risk, the summed up squared error, for the whole vector of estimates. Think of it over the long run. If you did this kind of combined estimation thousands of times with different sets of variables,
Right.
On average, your total error using the shrinkage method would be lower than if you just used the raw, separate measurements each time. Sometimes one estimate might be slightly worse, but the others improve enough to make the total result better.
So it's an average gain across the whole portfolio of estimates.
Exactly. And what makes it truly paradoxical is that all the standard trusted methods we learn, maximum likelihood, least squares, best linear unbiased estimation, they all lead to that obvious but suboptimal estimator. Stein essentially showed that our intuition and standard practice at the time was flawed in this specific scenario.
Which is pretty remarkable. So if the obvious approach isn't the best, what do we do? What's this James Stein estimator actually look like? How does it work?
Right, so Charles Stein and Willard James came up with a practical formula. The James Stein estimator takes your initial raw measurements, let's call them X,
Okay.
and it applies a shrinkage factor. It literally multiplies your vector of measurements X by a number slightly less than 1, pulling all the components towards a central point. Often that point is the origin, 0, or sometimes it's the grand mean, the average of all your measurements.
And how much does it shrink? Is it always the same amount?
No, and that's the clever part. The amount of shrinkage depends on the data itself. Specifically, it depends inversely on the squared distance of your observed data vector x from the shrinkage point.
So if my measurements are already really close to the center,
Then you shrink them more. The formula essentially says, these values are all pretty small, maybe they're just noise around 0, let's pull them in quite a bit.
and if the measurements are way out there, far from the center,
Then you shrink them less. The estimator sort of says, okay, these values are large, they're probably indicating a real effect, let's trust them more and not shrink them as much. It's adaptive.
that makes sense. It's like it's hedging its bets based on the overall pattern.
You could think of it that way. There's even a refinement where if the shrinkage factor calculates to be negative, which can happen if x is very close to the origin, you just set it to 0. You don't want to push the estimate past the origin in the opposite direction.
Right, don't overdo it.
And interestingly, this whole idea connects really nicely to something called empirical Bayes methods. Bradley Efron, a famous statistician, wrote a lot about this. It's like the data itself is giving you a hint about where the true means might be clustered, and the James Stein estimator cleverly uses that hint, even without explicitly stating a Bayesian prior. It kind of bridges the frequentist and Bayesian viewpoints.
Okay, that link is interesting, but I'm still stuck on this. Why 3? Why is the threshold 3 dimensions? 1 or 2? The normal method is fine, admissible. Add a third, and suddenly shrinkage is better. What happens at dimension 3?
That is perhaps the deepest mystery of the paradox. There's an intuitive geometric explanation and then a more profound mathematical one.
You try the intuitive one first.
Okay, so think about drawing a random point from a multidimensional bell curve, a Gaussian distribution centered at some true mean. In just 1 or 2 dimensions, your random point is reasonably likely to be fairly close to the true mean.
Yeah.
But in 3 or more dimensions, the geometry gets weird. Most of the volume of the space isn't near the center, it's further out. So a randomly drawn point is actually highly likely to be further away from the origin than the true mean is. There's just more room out there.
Okay, so the raw measurement tends to overestimate the distance from the center.
In a sense, yes. The squared distance tends to be overestimated. This bias grows as the number of dimensions increases. Shrinking the estimate back towards the origin helps correct for the systematic overestimation of distance inherent in high dimensions.
Wow, that's counterintuitive in itself.
It is. Now, the deeper reason, which Lawrence Brown proved in 1971, is mathematically stunning. It connects to the behavior of random walks, like Brownian motion.
Random walks, so a particle bouncing around randomly.
Exactly. In 1 dimension, a line, or 2 dimensions, a plane, a random walk is recurrent. That means, given enough time, it's guaranteed to return to its starting point, or arbitrarily close to it, infinitely often. But in 3 or more dimensions, a random walk is transient. It tends to wander off and has a high probability of never returning to its starting point. It just keeps exploring further out.
Whoa. So the fundamental nature of random movement changes at dimension 3.
Precisely. And Brown showed that the admissibility of the standard estimator, the MLE, is mathematically equivalent to the recurrence of Brownian motion in that dimension. Since Brownian motion is recurrent in 1D and 2D, the MLE is admissible. Since it's transient in 3D and higher, the MLE is not admissible, and something like the James Stein estimator becomes better.
That's wild. A property of random paths dictates optimal statistical estimation.
It's one of the most beautiful and unexpected connections in mathematics and statistics.
But what about the shrinkage point, the origin? You mentioned maybe shrinking toward the grand mean instead. Doesn't choosing where to shrink towards feel a bit arbitrary? Like, what if I just shift my coordinate system?
That's a very sharp question. On the surface, coordinate systems seem arbitrary. But in choosing one, and especially in choosing a shrinkage point like the origin, you are implicitly making a soft assumption. You're sort of suggesting that values near 0, or near the grand mean, are perhaps more likely, or at least a good central bet.
Ah, so it's like a subtle prior belief smuggled in.
In a way, yes. If you truly had no idea where the means could be, if they could be anywhere across an infinite range with no clustering, then your data point's x would likely be so enormous, so far from the origin, that the shrinkage factor in the James Stein formula would become essentially 0 anyway.
Making the James Stein estimate just the same as the original measurement.
Exactly. So the paradox and the benefit of shrinkage really relies on the fact that in most real-world problems, the parameters we're estimating, while maybe unknown, aren't likely to be scattered completely, infinitely, and arbitrarily. There's usually some reasonable scale or location, and choosing a shrinkage point helps leverage that implicit structure.
Okay, that clarifies the origin issue. So this bias, this tendency to overestimate distance in higher dimensions is key. Let's zoom out. How does this fit into the bigger picture of estimation? You mentioned risk, which often involves balancing bias and variance.
Precisely. Stein's paradox is a fantastic illustration of the bias-variance trade-off. It's maybe the canonical example.
Okay, refresh us quickly on that trade-off.
Sure. So any estimator has two main sources of error. Bias is how far off its average prediction is from the true value. An unbiased estimator gets it right, on average, like our standard MLE. Variance is how much the estimate jumps around from one dataset to another. High variance means it's erratic, sometimes close, sometimes way off.
So the standard method is unbiased, but potentially very jumpy, very high variance, especially in many dimensions.
Exactly. It's like a rifle that's perfectly sighted, unbiased, but shakes wildly in your hands. High variance. The James Stein estimator does something clever. It introduces a small amount of bias. By shrinking towards the center, it's no longer perfectly unbiased. On average, it might be slightly off.
Right, it's deliberately pulling the estimates.
But, and this is the crucial part, that small bit of bias is more than paid for by a huge reduction in variance. Because you're pulling everything towards the center, the estimates become much more stable, less jumpy.
So you trade a little bit of systematic error, bias, for a lot less random error, variance.
That's the heart of it. In high dimensions, the potential volume of where your estimate could land is vast. Shrinking cuts down dramatically on that potential volume, especially the far-out regions, leading to a lower overall mean squared error, even with the small bias.
The analogy you used earlier about the stadium.
Yeah, imagine guessing someone's location in a huge stadium, saying somewhere near the center circle might be slightly biased if they're actually near the goal line, but it avoids the wildly wrong guesses like up in the rafters on the opposite side. By restricting your guesses toward the middle, you reduce the chance of being spectacularly wrong, which lowers your average error overall.
That makes the trade-off much clearer. Okay, this is fascinating theoretically, but let's bring it home. For listeners thinking about data in their own work or life, where does this paradox actually pop up? What are the real-world ripples?
Oh, it's surprisingly relevant. Basically, anytime you're estimating rates, averages, or parameters for multiple groups or items simultaneously, Stein's paradox, or at least the principle of shrinkage, is likely applicable.
So not just wheat and candy bars.
Definitely not. Think about predicting baseball players' batting averages for the next season based on their current one. A player with only a few at-bats might have a very high or very low average just due to luck.
Right, small sample size.
Exactly. Shrinkage estimators, like the James Stein type, would pull that player's extreme average back towards the league average or the team average. And the fewer at-bats they have, more uncertainty, the more you shrink it. It gives a more stable prediction.
That makes intuitive sense. Regression to the mean.
It's a sophisticated form of regression to the mean, yes. Same idea applies to ranking schools based on test scores, estimating disease rates in different small counties, or even online product ratings.
Ah, the product ratings example, you mentioned that.
Yeah, a product with one 5-star review shouldn't necessarily be ranked higher than one with hundreds of 4.5-star reviews. You'd shrink that single 5-star rating towards the overall average rating for all products, tempering the estimate until more data comes in.
Makes the rankings much more stable and reliable.
Definitely. And it even shows up in cutting-edge machine learning. Techniques like ridge regression or L2 regularization in training deep neural networks.
Weight decay.
Weight decay, exactly. They essentially penalize large parameter values, effectively shrinking the model's parameters towards zero. In the incredibly high-dimensional spaces these models operate in millions or billions of parameters, this shrinkage is crucial for preventing overfitting.
So it helps the model generalize better to new data.
Yes, because as the saying goes, far from the origin there be dragons. Out in the complex regions of parameter space, models can fit the training data perfectly but fail on new data. Shrinkage encourages simpler, more robust models by keeping parameters closer to zero, embodying the same principle Stein discovered decades ago.
It's amazing how this seemingly obscure statistical paradox from the 1950s is still echoing in modern AI.
It really is. It tapped into a fundamental truth about estimation in high dimensions.
So we've journeyed from a baffling idea combining unrelated estimates, improves them collectively, to understanding the math, the weirdness of high dimensions, the bias-variance trade-off, and seeing its impact everywhere from baseball to deep learning. It really challenges our basic statistical intuition.
It certainly challenged the field when it was introduced.
So a final thought for you, the listener. The next time you encounter a situation where you're estimating multiple things at once, even if they seem unrelated. Pause and think. Is there an opportunity here to get a better overall picture by applying some form of shrinkage? Are you potentially leaving accuracy on the table by sticking to the obvious method?
It prompts you to question assumptions.
Exactly. What other statistical truths that seem self-evident might actually have deeper, more counterintuitive layers hiding beneath the surface? It's a good reminder that even in established fields like statistics, there are still surprises that can change how we approach data.